Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
Welcome to Chemistry Connections. My name is Jacqueline Sun, and I am your host for episode number 18 called The Chemistry of Lake Karachay. Today I will be discussing what is arguably the most polluted and undoubtedly the most radioactively contaminated lake in the world, Lake Karachay, as well as the chemistry behind what made it that way in the first place. So how did Lake Karachay earn its name as the most polluted place on Earth? Let's start with some context. Karachay is a small lake less than 1 square mile in area, located in central Russia in the Ural Mountains. In 1951, near the beginning of the Cold War, the Soviet Union dumped radioactive waste from the nearby secret nuclear facility, Mayak, into Lake Karachay. To pretty much no one's surprise, the Mayak reactor was built in secrecy between 1946 and 1948. Its purpose was to create radioactive material, primarily plutonium, which would allow the Soviets, who were feeling a bit insecure after the U.S. detonated the atomic bomb in Japan, to match the U.S.'s nuclear arsenal. Clearly, they succeeded because the Soviets successfully detonated their first atomic bomb in 1949, named First Lightning. However, as always, there were downsides. Besides the miles of land incinerated or permanently damaged, there was also much toxic nuclear waste remaining. Without regulation or regard for safety, the Soviet government directed for the radioactive waste either to be stored in underground tanks or to be disposed of in nearby water reservoirs. Lake Karachay was the closest lake to Mayak, which made it the primary dumping point. Understandably, from this point on, Lake Karachay's radioactive levels rose sharply. It accumulated 4.4 exabecquerels of radiation after the dumping. This is about 4 quintillion, which is a whopping 10 to the power of 18 becquerels, or 10 billion curies of radiation. For reference, the Chernobyl disaster released over 5 exabecquerels of radiation. And obviously, I'm not trying to make this into a competition, but Karachay was theoretically more dangerous because of the type of radiation that it released, cesium-137, which had a greater radioactive impact on its surroundings. And if you need any other convincing not to plan a camping trip to Karachay, in 1990 it was reported that standing by the shore of the lake for just less than an hour would provide enough radiation to kill you. Okay, so radiation clearly sounds like a great time. But what exactly is it? It all centers around nuclear chemistry or chemical modifications made directly to the nucleus of an atom. Nuclear reactions center around changes in the protons and neutrons located in the nucleus, which have the potential to release large amounts of energy. This is different from chemical reactions, which typically only involve changes in transfers in electrons. When the number of protons is changed, the element is changed from one to another. When the number of neutrons is changed, the element remains the same, but an isotope is created. These changes are called transmutations. Transmutation is often spontaneous or thermodynamically favorable because nuclei naturally seek stability or lower levels of potential energy. Think of this like the octet rule in chemical reactions, or how atoms will seek a full valence shell of electrons to reach their most stable state. Nuclear reactions will occur so that atoms may achieve a certain combination of protons and neutrons that stabilize the nucleus. So naturally, when an unstable nuclei releases protons and neutrons, this leads to its decomposition and the formation of a different nucleus. We can call this process radioactive decay or radioactivity. The often large quantities of energy released during this time that have the potential to kill you or at least severely harm you is called ionizing radiation, and it is in the form of alpha and beta particles and gamma rays, with the degree of penetration and strength increasing from alpha to gamma. An interesting fact about radioactive decay reactions is that they are first-order reactions. This means that the reaction rate is directly dependent on the concentration of the reactant or the radioactive substance. This also means that the rate of decrease in the concentration of the substance also decreases over time, because the reaction rate decreases as the concentration decreases. Due to this phenomenon, radioactive decay reactions have constant half-lives, which, if you couldn't figure out by its name, is the amount of time it takes for 1/2 of the number of nuclei in a sample of a radioactive substance to decay. To make it more complicated, different nuclear substances have different half-lives. For example, 100 grams of plutonium-239, which has a probably rather mundane half-life of 24,100 years, will take that amount of time to deteriorate to 50 grams of plutonium-239. And when another 24,100 years have passed, divide 50 by 2 and you get 25. In the case of Lake Karachay, cesium-137 was the main radioactive substance accumulated, which has a comparably shorter half-life of 30.17 years. After that amount of time, half of the cesium-137 decays into metastable barium-137, which has a half-life of around 2.6 minutes. After 2.6 minutes, metastable barium-137 decays to ground-state barium-137, where it is stable and no longer decays. During its decay period, cesium-137 emits radiation in the form of beta particles and gamma rays. These forms of radiation are high energy and very penetrative, which was what made Lake Karachay so dangerous. In fact, the radioactive substances in the lakebed of Lake Karachay irradiated over 500,000 people in a nearby vicinity. Many came into contact with it through everyday use, such as drinking or watering crops. And if Mother Nature wasn't already on their side, there was a catastrophe where a windstorm blew radioactive sediment dust over a wide radius, affecting many more. So how does radiation work? Besides causing much surface-level damage, such as burns, sores, and nausea, radiation can permanently alter the chemical composition of our DNA. DNA consists of 2 helical strands. An individual strand is supported by a sugar-phosphate backbone. Within this backbone are phosphodiester bonds, which are intramolecular covalent bonds that bind together the sugars and phosphate groups. Covalent bonds are formed by a relatively even sharing of electrons between 2 nonmetals. In the case of DNA, a carbon from the sugar is linked to an oxygen in the phosphate group. The 2 strands of DNA are then held together by intermolecular hydrogen bonds between nitrogenous base pairs in DNA. Pairs can only form between a pyrimidine and a purine base. Hydrogen bonds are formed between a hydrogen atom and a fluorine, oxygen, or nitrogen atom. However, the H atom must be bonded covalently to either a fluorine, oxygen, or nitrogen atom as well. In the case of base pairings, there will be 2 H bonds formed between an oxygen and an H atom, and 1 H bond formed between a nitrogen and an H atom. The cesium-137 radiation emitted by Karachay damaged the local residents' DNA by disrupting these bonds. The ionizing radiation first randomly knocked valence electrons out of their shells. The valence electrons could be more easily removed or ionized because they were a further distance from the positively charged nucleus and experienced more shielding, decreasing Coulombic attractions. As a result, the atoms became highly unstable ions. At such high levels of potential energy, ions underwent thermodynamically favorable reactions that disrupted the hydrogen and covalent bonds in DNA, inducing single and double-stranded breaks. This derailed the vital structure of DNA, leading to mutations, which then often lead to cancer due to the failure to undergo apoptosis or programmed cell death. At the time of irradiation, there had been a 41% increase in the rate of leukemia, 21% increase in the rate of cancers, and 25% increase in the rate of birth defects. Even today, the effects of radiation can still be seen. In the city of Ozersk, near Lake Karachay, the life expectancy is around 50 years, which is exceedingly low compared to the world average of 72 years. Even though its threat level was comparable with other well-known nuclear disasters such as Chernobyl and Fukushima, Lake Karachay is not widely known. In fact, information on it remained classified by the Russian government until the late 80s. The local residents of the lake had been in the dark about the so-called mysterious illness that had been afflicting them, not knowing that it was radiation poisoning. Lake Karachay shows just how impactful nuclear warfare can be even in non-war times and environments. and why steps should be taken to rid the world of nuclear threats and influence. Today, Lake Karachay is covered by cement blocks in an effort to prevent the further irradiation of the environment and nearby residents. Even if the incident is quite literally buried in the past, it is imperative to bring it to light to make sure the same mistakes are never made again. Thank you for listening to this episode of Chemistry Connections. For more student-run podcasts and digital content, make sure that you visit www.hvspn.com.